this last lecture, I actually have two topics. I mean, one is the probabilistic, and this will sort of try to amplify that different model, but on large scale, I mean, you have same type of generalized hydrodynamics. And there's one feature which I would like to explain to you is the fusion rule. I mean, this was something which I didn't know before and sort of appears in this model. And then there's the second half, and I'm sort of trying to sort of really put it, half of my time. I want to talk about soliton gases. That's sort of much more qualitative and sort of more, just displaying my own ignorance. But I think it would be nice, maybe generate some discussion and we can see. Okay, so then let's do first the probabilistic. I mean, I mean, this sort of, discretize the nonlinear Schrödinger equation. So it's CDT of psi. So psi, of course, we're always in one dimension here, and psi is now a complex valued wave field. And this will be governed by the x squared of psi. Okay, and then there will be a nonlinear interaction, which I guess I put here. So it's a cubic in the Hamiltonian, and sort of it's a quartic in the Hamiltonian, cubic in the field. And we're in the evolution equation, and then this plus sign is very important. I mean, so this is what people call the defocusing case, which sort of, if you think in terms of particles, means that the objects sort of repel each other. And then if there's also the focusing case, which on the basis of inverse scattering. Apparently doesn't make much difference. I mean, it's just sort of the minus sign, but dynamically, I mean, the minus sign looks totally different. I mean, it's a different world, and I'm not going to enter into this at all. And any one of these continuum models classically are a little bit singular, and it is sometimes convenient to actually sort of avoid these singularities by discretizing, and this is sort of what probabilistic did, and they said, okay, so let's look. I mean, now the complex field is denoted by alpha, and I put the I on the other side. I mean, so anyway, this is sort of, and then you write it like this, and then you put here the alpha of j minus 1 plus the alpha of j plus 1. Yeah. And the way you should see this is that, the one and this one is the discrete Laplacian, right? And the minus alpha j squared is now, a particular discretization of the nonlinearity. And if you do it in this way, it happens to be integrable. If you do something else, you might have put here just the alpha j or something like, for the nonlinearity, you just do the naive discretization. Doesn't work. I mean, this is a common feature. Okay, so now the next thing is, okay, so in here, I mean, the focusing case would be to put actually 1 plus alpha j squared, right? And there you can see that this is already very different from somehow 1 minus. And because you have the 1 minus over here, you require these variables. I mean, these are complex objects, but they have to be less or equal to 1. Otherwise, the equations of motion doesn't make so much. I mean, anyway, so this is sort of the setup. Okay. And I guess this object appears very often. I mean, so it's usually denoted by rho j squared. Okay, so now the first question is, what about the Lax matrix, right? Now, this was not discovered by Avlovitz and Ladek. See, they immediately did inverse scattering. But the Lax matrix, or the analog of the Lax matrix, which you know from the Toda, this was actually worked by so here comes the Lax matrix. This is worked by Irena Nenshu. Well, I guess she was a student of Barry Simon. I mean, he certainly push this topic very much. And there's another person which is sort of one Philip, which you know, we are using of when I explain. I mean, it's part of it is based on results by him, and this is sort of 2004 until 2007. I mean, they sort of worked on this problem, right? So this is Nenschel, Irena Nenschel, right? I mean, there's also a father Nenschel, but that's a different person. Okay, also a mathematician. Okay, so
what's the range of J here in the equation?
What is the range of what?
J.
Oh, here. Well, okay. Sorry. Okay, so this I took for granted. Okay, so here J is sort of the lattice index, right? And well, I will come to boundary conditions in a second, but I mean, this is just, I mean, okay. All right, so now the Lex matrix is based on these CMB matrices. So let me just don't write out the names, but I mean, CMB stands for Cantero, Moral, and Valesquez, and it's sort of, it's more or less at the same time. I mean, they were sort of studied independently, just sort of as an interesting mathematical object, if you want so, right? Okay, but and now I wanted to explain you this construction. I mean, it's sort of extremely simple. I mean, so you take a block, and you take a 2x2 block, and then you put into 2x2 block, you put here the alpha j bar, and here you put the vote j, and you put here the vote j, and then you put here minus alpha j. Okay, and in your head you can immediately sort of verify that this is a 2x2 unitary matrix, right? Okay, and now you do this construction, which everybody knows here because of sort of quantum many-body. I mean, that's sort of a standard thing which they do all the time. I mean, okay, so this is my J here, and so now you form these little blocks, right? And you have a matrix, and then you do this 2x2 blocks. Okay. Yeah. And let's say you define a matrix M by taking these blocks in this particular way, right? I mean, so this is my M. All right. And now if you want to sort of get some interaction between the blocks, I mean, you define a matrix O. The matrix O, I mean, simply means that you shift the blocking by 1 unit. Okay, and then your Lex matrix L is M. Now you have an interaction, right? So it's now it becomes a non-trivial matrix. Is that fair enough, or Sylvain, you're looking with question marks in your eyes?
Your block, you have only one J.
What is that?
This block, you have only one J, and then you act on 2 J's. You take the tensor product.
Oh. No. Where are you looking at? This block?
No, this block is fine, but then
the M?
yes.
So well, the M. I mean, I would think that I label. Then I put here maybe. I mean.
Okay.
This is the first block, right? And this would be maybe 1 and 2, right? And then I have the next block with 3 and 4, right? And then for the O, I just shift by 1 unit along the diagonal. Fair enough? No, I mean, that's the most important point. No, you still don't see it? Oh, okay. All right. So let me write it out more explicitly. Okay. So let's take a system. Let's take a system. Let's say 1 up to n, and n is even, right? Okay. So I make first the block 1, 2, and then I make the block 3, 4, and then maybe I do the block.
And the block 1, 2, J is equal to 1 or J is equal to 2?
No, J. I mean, this is this is a confusion. Okay. Very good. Okay. No. So here, okay, but here you put the index 1, right? And here you put the index 3, and here you put the index 5, right? This is okay. No. Okay, I excuse myself. Maybe I should have explained this. Right? Okay. And now here you do exactly the same construction. Of course, I mean, you think here in terms of periodic boundary conditions, let's say at least in this picture, and this gives you the matrix O. Fair enough, or still okay. So then I of course you get a non-trivial matrix, and then you can see that you know this when you do this multiplication, then of course you know this is a tridiagonal matrix. But if you do the multiplication, you see that you get whatever a quindiagonal. I mean, you know there you have two further off diagonals appearing when you do the multiplication. Fair enough. Fair, or still not so happy?
No.
Hmm? Okay. Anyway, so this is one special case of you know a class of quint diagonal matrices which these people studied. Okay, so now okay, comes sort of the boundary condition which you have to put. And so let me put here the boundary condition. So you have, I mean, you have the periodic boundary condition, which is sort of obvious thing, right? And then you can also have have what people call the open boundary. And now the open boundary, you know, it's sort of a little bit less obvious. I mean, so you know, how do I impose the open boundary? Well, I mean, you know, if you study this subject, I mean, then what you find is that the natural choice is that let's say you put alpha 0. I mean, okay, I take now 0 up to n. You put here on one side you put. You fix the two fields at the two sides simply, right? I mean, so the usual choice is, you know, you can take a global phase, which doesn't make any difference whatsoever, right? I mean, but so I fix the alpha to -1, but the alpha n, this is for even n, I guess I put it equal to fine. Okay. So you fix them with absolute value equal to 1, right? All right, and then well, then you know everything goes through. I mean, so I don't really repeat you know the story, but I mean, for instance, you know when you look at the conserved fields, okay, so we have the conservation laws. You know, this would be simply Q. I mean, the density is simply the trace of my Lax matrix to the power n. And you know everything what I told you in the last 2 hours, I mean, just sort of goes through. I mean, you see that this is something which is not necessarily real. I mean, so you know you have to take. I mean, it's not a symmetric matrix, so you have to take, so to speak, the real and imaginary part, right? I mean, and but then you know everything goes through. I mean, so and then there's also the Q0. Which will be, in this case, I mean, the log of OJ squared. Yeah, okay. Well, maybe I should have written here the density. I mean, okay, so anyway, so this is the QJ. Maybe I should have written here the density. I mean, so this just L to the power n, and then the J's matrix. All right, so I don't want to go into this. I mean, so at the end of the day, you know, it looks just exactly like Toda, but now, of course, the spectral parameter, which in the Toda, because the Lax matrix was a symmetric matrix, was on the real axis. This is now, of course, you know, it's a unitary matrix. So that's now on the you know spectral parameter, which I call here then C, and the C is some point with just a phase, I mean, which is sort of have absolute equal to 1, right? And that's the only difference. And so when I write down, you know, the density of states, of course, it's the density of states on that unit circle, right? And if I write down my hydrodynamic equation, then, you know, it will be, you know, locally the density of states on that unit circle. Okay. So there's one thing which is missing. I mean, so you know, for the phi theta, we found that okay. So what is missing is still the scattering shift. Well, I mean, for the phi theta, I mean, you know, we had this twice times the logarithm of lambda j minus lambda j prime. Where these were, you know, the spectral parameters of the two quasi-particles. I mean, so that's fine. And so over here, of course, I mean, this cannot be the answer, but you get something which is sort of almost the same if you want. So it's the ARL, and it will be the logarithm. So again, you know, I have the shift of two objects, let's say with spectral parameter C and spectral parameter C prime. And it will be nothing else but C minus C prime absolute value squared. So if I want to make it really analogous, I should have written it like this. Okay? So the most trivial simple modification, which you would sort of expect if you're on the unit circle, is the spectrum shift. And then the rest is just the same. Okay? All right. So now, well, unless there are any questions on that stage, I mean, I'm not going to display any formulas anymore, right? I mean, for that case. The only thing which I wanted to point out is that, you see here, the scattering shift, I mean, I know very well. I mean, I just take these two particles. But what is scattered in this case? I mean, it's on the unit circle, right? I mean, which object is actually scattered? Now, of course, you know, because I get the formulas in the write down the TBA, it's clear that it's a scattering shift, but it's a scattering shift of what? And so this is I want to explain to you. Okay, so this is something which I did. I mean, with Alberto Bordo. I mean, he's doing his PhD in Munich. He worked with master with Pascal actually. Anyway, so you know, I was puzzled by this. I'm asking, you know, what is scattering, and so we figured out what is scattering. Okay. All right, and so of course there's one simple hint, if you want, so that in the case of the open chain, when you look at the limit at c going to infinity of the field, you know, with index j here. Then if you look up the literature, I mean, then you find that this is equal to. So now these are the C's are here always the eigenvalue of this unitary Lax matrix. And since I have a system of lengths n, I mean, you know, it starts with capital N. And then it goes down to n minus 1 plus j. And I have to take the complex contribution. This, let's say, I call it C tilde. So, you know, these are complex numbers of absolute value 1. I mean, these are phases. And therefore, of course, you know, this is also phase. So this is what you find in the literature. So from there, it's somehow clear. But the higher horizon is, you know, to which you scatter should be the unit circle, right? So the horizon is the disk, the unit circle I need. Okay. All right. So somehow you would think that that's related, and now Alberto discovered, you know, this simple transformation that you put the alpha j equal to the square root of 1 minus e to the minus rj. So rj is, let's see, I have to put the phase and e to the, I just want to get the right sign, I theta j. And this turns out to be a canonical transformation. And I mean, this is 0 pi, but you know, the rj is greater or equal to 0. Okay. And then in the new variables, I mean, you can write down what is the Hamiltonian. which is then the square root of 1 minus e to the rj, and square root of 1 minus e to the minus rj plus 1, and then now the phases come in as phi j minus phi j plus 1. I guess I have theta, so I have theta j plus 1. Okay. And now the objects which scatter are the RJs. I mean, so the RJ, you know, is sort of the analog of Qj plus 1 minus Qj. And of course, you can translate everything in terms of to the actual positions, and it's those positions which scatter. Right? And once you do this transformation, then you know you get the usual picture. I mean, the one which for the toda, you have these particles which are sort of moving. Of course, you know the momenta are sort of more these phases, so you know they sort of lie on the unit circle. But otherwise, you know, it's sort of the same, and you can also figure out, you know, what is sort of the asymptotic velocities. I mean, the asymptotic velocities are actually, you know, if I take the quasar particle with spectral parameter c on the unit circle, I mean, and then the velocity is simply it's a sign, it's I sine, so it's j bar minus j. All right, fine. So at the moment, nothing terribly new actually appears. But now let's do one thing, namely, let's look at the case. Okay, so here, you know, the Hamiltonian which I studied was the trace of C plus C star. You know, if you look at all the definitions, and then you discover that you will get, you know, the Hamiltonian corresponding to this time evolution, right? I mean, so you know, I sort of, if you want to, this sort of the simplest possible Hamiltonian I could look at, right? But now, you know, since you know, I could also do the Hamiltonian which is given by the trace of C minus C star. And then maybe I put an I in front so that it's a real quantity. Okay, so it's just a slightly different Hamiltonian. And this is in the literature, this is called the show flow. I mean, for some reason, which, well, you know, it's always good to have some names, right? I mean, so it's apparently, I mean, it's not sure who wrote it down. I mean, you know, I mean, somebody wrote it down and then somehow sure polynomials appeared and then they call it sure flow. Okay. All right, so that's this thing. So let me write down what the evolution equation is. Alpha j is equal to, so it's again the rho j squared. Then you have the alpha j plus 1 minus alpha j minus 1. And so it looks a little bit different from this one, but otherwise not so much, right? Okay, but now comes the point, you know, you look at this equation, there's no I anymore. Of course, I can start with, you know, sort of complex initial data and look at this. And then, of course, you know, the whole story, which I said over here, sort of somehow repeats. But what I could do is I could also start with real initial data. Okay? So let's take alpha in the interval minus 1, 1. Well, it stays real. This is a set of mesh 0. So I have to redo the whole story, right? I mean, I cannot just sort of copy what I had over here, right? I mean, and now you see, if I do this, I mean, then you look at your spectral parameter. You see, now the matrix is unitary and it's real, you know, because I'm just multiplying real numbers, and therefore, you know, the spectral parameters is twofold degenerate. I mean, if this happens to be a spectral parameter, then automatically I must have also this spectral parameter. And so I have a twofold degenerate spectral parameter. And if you look at the way how you would compute you know, the asymptotic velocity in this case, then you see that it's C plus C bar. And so you see that, you know, the twofold degeneracy, so, well, I mean, twofold degeneracy. I mean, you have this particular degeneracy, but when you look at the velocity, which is c plus c bar, then you always have two quasi-particles which have exactly the same velocity. So the conclusion is that you form bound states in this system. Right? So we have bound states, right? All right, and so, you know, when you look at our usual scattering picture, I mean, so here I have, let's say, my j, and here I have the time t. So here it's mushy, I don't know what's happening, but, you know, if I sort of wait long enough, I mean, then what I will see is that these particles are sort of moving out in pair. And of course, this distance is sort of, you know, there's a formula. This distance is sort of, I mean, the velocity is what I've written down here. And this distance is sort of, you know, fixed by the spectral parameter. It's some formula which one can write down. Okay. All right, so that's fine, and then of course in time to infinity. I mean, you know, I get the same. Well, I get the same object here, time to infinity, and of course, you know, now the question is, how do this? You know, what is the scattering shift of these bound states now, right? Okay, so maybe I can save a little bit of space and do this over here. Okay, and so this is where the fusion. Okay, maybe I should tell you the story. You see, I mean, this you know, I mean, this part which is sitting over here, I worked out. You know, sort of maybe 4 years ago. I mean, I guess there was also sort of parallel work by Tamara and Guido, and anyway, but then, you know, I also looked at this case, and then I found sort of scattering shifts which look different. I mean, they you know, when I looked at them, you know, they did not have the rules which I was used for scattering shifts for the total lattice, and so I was, you know, I said, you know, how come? I mean, you get these funny scattering shifts, but the answer is that you know, you have to compute the scattering shifts now using the. So I had no way of really, you know, since I didn't know what scattered, well, I couldn't really properly interpret the formulas. But the solution is that there's something which is called the fusion rule, which tells you how to do the scattering shift. And so let's see. So okay. So maybe so here I have one pair here, right? And maybe here another one. And let's see. So maybe this is. I mean, so I'm looking at this. This has sort of an e to the I theta. Let's say as its sort of spectral parameter, right? And then I want to study this, the scattering of this one, but then it scatters with a pair, which has then here a phase I to the theta, and here a phase prime. I mean, I want to have a different one, and minus I to the theta prime, right? I mean, this is a pair. I mean, you know, it has a spectral parameter, the C and the C bar. Okay, and now the claim of the fusion rule is that what I should do is I should do the scattering. You know, I should add the scattering shift coming. So I'm looking at this one, and now I get the scattering shift from this collision. Okay, that's fine, and then I should add it to the shift of the partner in this pair, right? And so the fusion rule in this particular case would say that I take the log of e to the let's say I theta prime minus e to the I theta. That's the formula which I have cleverly erased. Now it's still sitting here, right? And I take the square of that. And then I add the scattering shift of e to the, and now, you know, the theta stays, but, you know, I have to put here the minus I theta prime minus e to the I theta. Okay. And if I do this, and if I use the fusion rule, then everything comes out exactly as you want. It's a little bit surprising, it's sort of, but I mean, this was discovered, I mean, the fusion rule was discovered in quantum mechanical models, I guess, in spin chains, and people sort of observed this already, so I don't think it's a such sort of a novel insight. But the main point is that if for this particular dynamics in the Aberlitz-Ladek model, it's this fusion rule which appears, and I don't think that there's any other sort of classical model where this has been observed. Okay. So this ends my part on the Aberlitz-Ladek. I mean, I have questions. I have to raise the board. I mean, so the questions I'm happy to answer. Of course, there would be many more things to say, but since time is limited, I thought this is sort of the most interesting feature. Okay. Okay, so now I want to talk about soliton gases. And okay, as I said, I mean, this is a sort of just tries to open some discussions, and so now I come to the point, fear point. All right, so I have to go back to the system, where this sort of were discovered first. I mean, this goes back to the 60s, and this is called the vector phase equation, and this is a PDE, or sort of nonlinear wave equation. I guess I put here a plus sign now anyway. I mean, there are some people who put here a minus sign. I have this here, and then I have a cubic derivative. So this is a real wave field living on the real line. Okay. And this also has a Lax matrix. It's just an L, which is minus dx squared u. So, well, sorry, it's like this. Okay. This, okay. I mean, this is second derivative. That's a Laplacian, and this is of the potential, right? And that's a linear matrix, linear operator now, right? Okay. All right. So and then people discovered that there are objects which sort of well, okay. So maybe I should say that what they discovered in our language is that sort of corresponds to the quasar particles, right? And this was discovered. Actually, the first indication was discovered by numerical simulations. I mean, this was done on very primitive computers, but what people, of course, I mean, what people knew already for a long time, that you had the soliton solution, so that was a propagating wave with sort of just a peak like particular sort of peak like this. I mean, yes, it's 1 over cos squared is sort of the form which it has, right? This sort of just a traveling wave. But the point is that in order to check integrability, of course, they wanted to see that you have sort of the scattering, and what they discovered in our language would be the scattering of solitons is just exactly what you know from quasar particles. And so they had they did a simulation with I don't know 3 or 4 sort of they just put it on the initial conditions, sort of like a few solitons isolated from each other so they wouldn't overlap, and then they just solved the PDE, and then they discovered that what you expect for quasar particles particles, well, in our language now, was actually numerically confirmed. And from there on, I mean, it was clear that it should be integrable. And then, of course, the whole industry we started, which don't want to go into. Okay, so now let me make a bold statement. So I put some, I mean, I expect opposition, but maybe we can do this after the talk, right? So let's see whether people agree. Okay, so I'm trying to say that in quantum mechanics, what people would call solitons are merely bound states. It's a phenomenon just like what I have over here, right? I mean, quantum particles can form bound states. I mean, these are sort of the string states well of magnons. So anyway, I mean clearly any quantum mechanical system can sort of has the possibility of forming bound states, and then in integrable systems these bound states sort of can behave like quasi particles. Okay, so I'm trying to say that in quantum mechanical systems, there's sort of no distinction between, what we call here solitons, which have sort of an internal structure, and quasi particles. I mean, of course, if I take the delta Bose gas, then it doesn't form bound states, but that's fine. I mean, that's a particular simple case. I don't have an index which sort of has to count which particular bound state I'm looking at. But if I look at an XXC model, let's say, then the magnons will form bound states. I mean, the so-called string states.
Even the Bose gas for attractive interaction.
Yeah, no, yeah, that's right. Of course, also, yeah, no, thank you for pointing out. I mean, this is what I emphasized before. I mean, it's a defocusing case. If I make repulsive, then I just don't see bound states. If I make attractive, there are bound states, and one has to sort of, yeah, absolutely correct. Okay, so you have the string states. Okay, so this is fine. Okay, but now we want to go back to the classical world, and then of course somehow it's I mean somehow there seems to be sort of a distinction between what we studied before and the solitons, and so somehow I want to say a few words about this distinction. Okay. And now, luckily enough, we can go back to the Toda chain.
So sorry, bound states. I mean, do you mean like a localized state, or
no bound? Yeah, localized state. It's like a little molecule. I mean, quantum mechanics. This would be the simplest sort of.
Like the beta eigenvector that's kind of.
Yeah, well, but it's an eigenvector of let's say 2 or 3 particles, right? Yes. But that eigenvector can okay. It's just saying that this quantum object has an internal structure, right? It's sort of made up of whatever 3 or 4 particles, right? It's just okay. No, it's just. The hydrogen atom is a bound state of an electron and the nucleus, right, and the proton, right? I mean, it's just exactly in the same language. Okay. All right. Okay. So now now we have the Toda chain, and of course, I mean, Toda discovered the one soliton solution. Yeah, now I can sort of explain this. So I mean, maybe I want to write down the formula. Of course, I can write down the P's and the Q's, but I want to sort of have a simple formula here, and so let me just display this omega squared. And so actually, it's really very, very similar to the KdV equation, and you find cos squared here. Yeah, that's this one over here, and then you just have the traveling wave. I mean, so here's an eta j minus omega t, and maybe some extra shift, which is irrelevant here for my purposes. Okay, and the omega of eta is in this case sinh of eta. Okay, So you see the velocity, you know, I have to break it out. The eta absolute value is then the omega divided by eta, and therefore, you know, the soliton speed is actually greater than 1. Right? So these objects move sort of faster than sound, so to speak, right? I mean, if you want so. All right. Okay. Now, of course, you know, after you had the one soliton, I mean, people had the n soliton, and then of course you verified that, you know, their scattering behavior is exactly like quasar particles. Okay, and you can go a little bit further. I mean, you can well, maybe I should have said this before. I mean, you know, one can, as a next step, I mean, you look at the two soliton. I'm not writing down, but I mean, all the things so can read. And from the two soliton, I mean, you will compute the soliton scattering shift. Which is different from our log lambda minus lambda prime. You know, these objects, obviously, I mean, they have different scattering shift because they have an internal structure. I don't want to write the formula because, you know, it's not so instructive, but, you know, you have sort of, you know, something this. I mean, this one goes fast and this goes slowly, then you have sort of an overtaking, or you can also have the collision between the two solitons, right? I mean, so, and you can write down the formula for the, okay. And so, and then, you know, once you have, you know, the formula for this, let's say two solitons, I mean, then of course, you know, this is how they behave, but then you look at there's then an n soliton solution. And then you can look at the asymptotics of this n soliton solution. And of course, what you find is that, you know, asymptotically, they will have, I mean, you know, when I write n soliton, you know, each soliton sort of is constructed, which something, well, let's say I look at this n soliton solution, I look sort of at very long times, you know, then they separate linearly in time. And I look at one of the member of these things, I mean, this will, of course, will have that particular thing, with its own intrinsic eta. And then you ask about the scattering shift, and then it's given by the rules, as we know from the quasar particles, right? So no surprise whatsoever. Okay. So now you see, but now we have the Toda chain. So you might ask yourself, you know, how is this related to the Lax matrix, and you know, what is the kind of situation? Well, okay, so that we can do. That we can certainly do. So now I look at the Lax matrix. Okay. So now what is now the Lax matrix? Well, of course, the Lax matrix is the old Lax matrix, which I always show to you, right? It hasn't changed. But you see, when you look at these particular solutions, I mean, you see, I put HJ squared minus 1, right? And also, you know, when I look at these Endholz solutions, I mean, it's clear that you know, these are objects living on the infinite lattice, and therefore the Lax matrix which you have looks like this. I mean, so the Lax matrix is still sort of, you know, our tridiagonal matrix, but at infinity, you know, at infinity it will look like this, right? I mean. And then, of course, I have somewhere some perturbation, and in the other infinity, it will also look like this. You see, this is basically what this is the one over here. So I look actually at solutions of my Toda equations with very specific boundary conditions at infinity. And so, you know, in a more physics language, what you are doing is um, you're looking at we have distinct vacuum. So it's, for the quasi particles which I discussed, it's basically whatever, empty is sort of vacuum, right? I mean, no particle. And then I put one particle after the other. These are sort of the excitations of that vacuum, right? And if I do the solitons, then the vacuum is, so to speak, the Lax matrix, which is just sort of the silver one, right? The max, sort of silver is that well, I mean, the one which I'm plotting over here, right? I mean, which is sort of equal to this wide diagonal matrix, silver 1, 1. Okay. All right, so now you can say, okay, what about the spectrum? Well, of course, if I now do an excitation over here, then the spectrum which I find is sort of just these n eigenvalues which I discussed in the first two lectures. But now when I do the spectral theory of this operator, and I remove the L0, but I go to the L, which is a local perturbation of this one, I will have a spectrum which is very different. So now the spectrum of L looks like this. I mean, so this is it's still a symmetric matrix. So and maybe I should have put here 1/2 anyway. So this is not so important. So you will find absolutely continuous spectrum which goes from -1 to 1, and then out here you will find some eigenvalues depending on what you do, right? I mean, there's no eigenvalue inside this continuous spectrum here. Okay, that's the spectral theory of Jacobi matrices, all right? And now, when you look at, I mean, for instance, the work of, well, there are many people, of course, which have worked at these things, but I think that the most complete results are also given by Teschel and co-workers. I mean, this is sort of, roughly 2010, I mean, something of that order, right? I mean, it's not, it was not done in the Asian time. And of course, it's sort of, I mean, it's a lot of in-between developments, I mean, whatever, Riemann-Hilbert problems and all kind of things. I mean, it's a long technical story, but I just sort of want to sort of say a few words about what looks important to me in this context. So what they say, what they look at is initial conditions which sort of satisfy decay. So this goes over the whole lattice. I mean, it's 1 plus. So basically, they're saying that asymptotically, we put here, the initial momenta sort of have to go down to 0. I mean, that's just sort of what it's indicated over here. And the other one is the HJ, I guess it's -1/2 absolute value. And this should be finite, right? I mean, so this is sort of, the precise condition of what is sort of meant by perturbation of that particular vacuum. Okay. And then for this, I mean, they show that that these things actually produce for you solitons. So I take some, let's say, fairly general perturbation, and I maybe I have sort of 10 of these eigenvalues. And then, what they're saying is, if I look at now at the solution of this thing, asymptotically, they will go, with the particular velocity, which you actually wrote down maybe somewhere. Yeah, the velocity of these solitons. I mean, just sort of give you an impression. I mean, it's given by C minus 1 over C. I mean, C is the spectral parameter here divided. Maybe some transformation. No, sorry. Okay, maybe I should. No, just give you the correct formula. Okay. So the spectral parameter, it's still denoted by lambda. That's sort of the eigenvalue on the real axis. And then if you want to actually compute what is the velocity, I mean, then you have to do this transform here, the lambda minus lambda squared minus 1, and then the velocity will be c plus c minus 1 over c divided by 2 times log c. I'll just give you at least one formula so that you see that things are quite explicit, right? Of course, you first have to solve the spectral problem, but given the spectrum, I mean, then I can sort of write down these things. Okay, so that's fine. Okay, but then there's also this piece here, right? Now for this piece, this is in the physics language. I mean, okay, so maybe. Okay. Okay, so in the physics language, this is called radiation for whatever good reason. When you look in the sort of earlier literature of Toda, which of course, knew about these things, maybe, of course, he did not have any results of that sharpness, but, I mean, the mere phenomena which I'm going to describe here, I mean, was understood by Toda very well. He calls it ripples. Okay. Now, what do they look like, right? I mean, so this is you can find numerical simulations, and then sort of I discovered them only sort of maybe half a year ago or so, but I sort of found them very interesting. I mean, so when people talk about a radiation, I never had sort of a real physical picture of what they look like, but so now you see what I'm plotting is now just taking rather simple initial conditions in such a way that in fact, well, I guess the initial conditions which I looked up, it has basically one soliton. So there's just only one eigenvalue, and then there's sort of continuous spectrum, right? I mean, so this you always have, right? Okay, and the way how it looks is the following. I put here J, and then I have here T, and then of course you have the light cone, right? I mean, so you have the light cone, and of course if I let's see. No. I want to put here. Okay. Since I want to put the PJ over here, you still can put the light cone here. Okay. And I'm looking at large P. Right. And now the soliton will travel with the velocity which is larger than 1. And then at large time t, I mean, you basically in this picture, I mean, you will see sort of like a peak over here, and it's extremely narrow. I mean, it's well, I mean, for there, I mean, these solitons, if I don't make I mean, if the velocity is very close to 1, I mean, then they become broad. But if I make it a little bit larger, then there are sort of really spikes. Okay, so let's say I have this. So this is the soliton. Okay, and then let's say this is sort of the time when I'm looking at. I mean, so this would be sort of t in this units, right? I mean, so that's velocity equal to 1, and then you will see, then you will see something over here, which sort of, at least in the picture, sort of has a shape like this. Okay, and then of course goes symmetric down here. And you might wonder, what is sort of defined structure? The defined structure is that you should think of a lattice for some sort of highly oscillating function. We sort of looks then random-like because it's after all the PJ is sort of still defined only on the lattice, but then it has sort of extremely well-defined envelope. And in this envelope, I mean, people from whom I took this, I mean, they, you know, of course, you know, they were so familiar with this, and you know, they didn't even try to check, you know, whether their envelope sort of agrees with any kind of formulas. But when you look at Heschel, I mean, he gives you also not only the asymptotics of the solitons, but he gives you also the asymptotics of what we would call the radiation, right? And then you know, you have to use a little bit the computer, but then you find, you know, what he would predict for this particular shape, and you know, it just fits perfectly. But you see, what he also predicts is that this soliton will feel a little shift from the radiation. You know, I mean, the soliton will not be exactly linear, but will sort of moving with a particular shift. Okay. Okay, so now, you know, we want to, now the big question is, you know, can we do generalized hydrodynamics in this kind of context? And of course, you know, I cannot give you any answer because we don't really know. But what it looks like is that what seems to be the case is that you have sort of like well, so maybe I indicate this as a guess. I mean, so you see what you should have is really a coupled system. So, you know, if I just take the soliton component, I mean, then it will do, you know, what we know more or less already, but in general, presumably it will be a coupled system of quasar particles. Solitons plus the radiation. And well, we can make guesses anyway. It's just something which sort of looks plausible, you know. Which way it comes out, we don't really know because you see, I mean, this result, I mean, of Peschel, I mean, of course, it's for deterministic initial conditions, and we really would like to have random. Okay, so I'm finished. So let me say that there's just sort of only one word at the end here. You know, there's a sort of famous work by GHD. And you see, there's this community of soliton gases, which is a big community. I mean, it was sort of, you know, sort of years ago, I was at some workshop in Cambridge, and I was impressed. I mean, they do all kinds of things in France. They have water tanks where they sort of study these soliton gases experimentally. You know, it's a big community, and one of you know sort of important persons is GHD, and he had already in 2003, I think this is correct. Yeah, in 2003 he published Fischer's letter where he proposed, you know, what would be sort of like a hydrodynamic description of a soliton gas. And surprisingly enough, I mean, he looked at a situation where there are only solitons. I mean, there was no radiation, and he came up with you know, exactly the same formulas as what I showed you from generalized hydrodynamics. Okay, so it has exactly the same structure. I mean, you just take the two-particle soliton scattering shift, and the rest is sort of okay. Now, this is a complicated paper for me, at least, sort of, you know, because it takes sort of somewhat singular limits, and then but anyway, I mean, it's a fact that you know, the result at the end which he gets really coincides with what you would have naively predicted on the level of generalized hydrodynamics. And why is the paper so difficult? Is that well, I mean, first of all, he had to take a limit in order to get rid of the radiation, right? I mean, so and that's sort of somehow, you know, a singular limit, because when you just write on sort of some arbitrary random type of perturbation, I mean, then you know, you will always get this mixture of continuous spectrum and solitons, right? Okay, so this one, but then the second difficulty, which I mean, I still, people have written articles about this and try to explain this, but to me, it's really somehow a central problem, which the moment I have nothing positive to say, actually, is that. Okay, so this is soliton gas. And the question, what is the GHD? So I put this with 2 question marks that everybody sort of understands that it's not an assertion, but I simply don't know what the GHD are. Right? You see, the point is about when I do the standard thing, the quantum systems, I do my total lattice or other classical system, which is sort of based on quasi-particles, then I have immediately a formula for the GHD. Now here, for the solitons, I mean, of course you can say, okay, I take here some initial condition, and then I put here a soliton, and maybe this distance I make random, I put another soliton. But you see, it's a very ad hoc. I mean, it's presumably correct to some extent, right? But it's a very ad hoc type of object. And it would be nice if there would be something sort of like a GHD, but that's sort of a little bit. If you look at the literature, I mean, they mostly try to say that maybe I can put this comes with a parameter. I can make this parameter random and this distance random. It's sort of like doing something which is random, but without sort of a specific structure like what we know for the case of solitons, where we have, because we have Hamiltonian systems, we know how to write down sort of invariant measures. Anyway, the time is up, and thank you very much for listening. It's always good to end the talk with the question.
So the GHD for the bound state case.
For the bound state.
Yeah, so if I go to XNC states,
yes,
you want to think of them as solitons. I can do
no, yeah, but okay. If I take XC, I mean, then I do quantum mechanics. I mean, then I have string states, and once I have string states, and then I write down, I write down my e to the minus beta of the conserved quantities, and then there's no, I mean.
Yeah, but it doesn't give hints.
Yeah, but you see, I mean, this is what I was trying to say. I think these soliton gases, I mean, the way how it's sort of described over here, sort of, I don't think they have a direct quantum mechanical analog.
I thought that's what you were claiming.
No. I was claiming that for quantum systems, there's only the standard quasi-particle sort of generalized hydrodynamics, with the understanding that you could have that you might have a much more complicated structure than what I displayed here, because you must keep a further parameter which keeps track of the bound states. So you see, if I do magnons, I mean, then you will have bound states of arbitrary lengths, and so you have sort of an extra parameter which tells you which bound state you're actually looking at. So it's clear that when you write down the generalized hydrodynamics, I mean, you must have at least one other parameter which appears in the equations. And you must know, I mean, what is the scattering shift if I take a bound state of, let's say, something of 5 bound magnons and 7 magnons, and they collide. I mean, you must know how they actually do these collisions, right? So I was trying to say the opposite, that on the quantum mechanical level, there seems to be there's nothing like this over here, right? This, okay. This is what I was trying to say. Yeah. But well, maybe it's just sort of another word. Sort of, when you look spectrally, I mean, then at least on that level, you can understand that I'm looking at 2 very different cases in the classical. I mean, let's say for the total lattice, right? and how they are sort of interlaced, I mean, that's sort of not so totally clear. Yeah, very good. Okay.